Okay, next up we have Thibault Bertrand from Imperial College London, who is going to be speaking about disordered yet directed particles.
Well, first I'd like to thank Luke, who just, I think, stepped out. I'll thank him again at the end for inviting me to talk at this meeting. It's great to be back here at the Isaac Newton Institute. It's always really enjoyable. So today I'd like to talk to you a little bit about flocking. And although the Vicek model and other works on flocking started 30 years ago, I hope to convince you that there's still some surprises in there to be found. It's work that we've done with Eloise. Hopefully, Eloise, you won't have any questions. Raphael and Sylvia, who are both from Paris. So in the group, we're generally interested in sort of all things active matter, going from sort of single particle problems, and I love the fact that, Rob, you said earlier, there's lots of cool physics to be done, even on single particle problem. But today, what I'd like to talk to you about is about systems in which you've got emergence of collective behavior. So I'll be talking to you about a particular type of phase transitions in active matter, and that's coming out of a story that we just put on the archive and submitted a couple of weeks ago, so it's fresh off the press. Okay, so sorry, Rob, I had to do it. You've got what we're talking about today is active matter. So active particles. Everybody in the room probably knows that those locally consume energy to perform some function. The function I'll be talking about today, and I'll basically stay in that class of system, is self-propulsion. So it's using that energy to self-propel. You find them at all possible scales, but really what I'll be talking about, well, the model that, the system that inspired the model that we have today is sort of these macroscopic schools of fishes or flocks of birds. That's the primary motivation. And the really big picture motivation is the fact that non-equilibrium features really emerge from the interactions between particles. And when you've got a single particle, they also emerge, but from the interaction of that particle with its environment. So today we'll be talking about swarming, flocking, and long-range order. And about 30 years ago, almost, there's been the realization that simple alignment interactions between particles in these active systems can lead to long-range order. So the system of motivation, as I said, was the flock of starling in the original work by John Toner and Thomas Vicek. And this Vicek model that came out in 95, which has been recoined a couple of times, flying XY model, is a very simple model where you've got a set of point-like self-propelled particles. They are basically only interacting with their neighbors through an alignment type interaction. So they try to align with neighbors that are not too far away from them. So within an interaction radius of say size sigma I here, and except for that, they just self-propel at constant velocity v0. Originally, Thomas Vicek wrote it in a very discrete time formulation that was easily implementable on the computer. But over the years, there's been reformulations of it, and the formulation that we'll adopt today is that continuous time formulation. So each of these particles here has a heading, which makes an angle theta I with some reference axis. Pick x, for example, the x-axis, and is characterized by its position Ri. So the velocity of the particle is just this advection term here. They're moving at a constant speed along the polarity vector pi, and the direction of that polarity vector is actually changing over time according to this Langevin equation. You've got a first term that corresponds to the alignment interaction with the neighbors. This is what we call a mean sign type alignment. And the reason we call it a mean sign type alignment, because you've got this prefactor 1 over ni here, which is the number of neighbors that you're interacting with at any point in time. So it's basically the size of that set ni of neighbors that you've got. And the reason why you put this in this model is because people, after doing very large-scale simulations, realized that these systems were riddled with finite size effect, and there was a lot of clumping in the system. So you've got large density fluctuations that arise from these interactions. One way to tone that down, to be able to do proper characterizations of phase transitions, even numerically, is to put this in. So we added in. And the second term here is a noise term, where eta is a characteristic noise strength, and that Ci here is just a Gaussian white noise, okay? Zero mean standard deviation equal to 1. So that's the classical V-check model, and what's classical about it, in a sense, is that that coupling strength here, K, is a constant. Everybody interacts with the neighbors exactly the same way. And there's already quite a lot of nice physics in there, so if I actually put them in a simulation box of size L, I make the simulation box doubly periodic, so I can, on the computer, simulate an infinite size system. What I will see is that if I place myself at large enough values of the coupling strength, so they tend to align quite strongly, you will have a flocking state, okay? You'll have breaking of rotational symmetry, that's spontaneous, and that is in clear violation of the equilibrium Mermin-Wagner-Hohenberg theorem that says that normally in a 2D XY model, you shouldn't have long-range order phase at non-zero temperature. Okay. Now that transition here has been debated for years, for the best part of the past 30 years. In particular, there was a lot of debate around what type of transition that was, whether it was continuous, discontinuous. I think it's fair to say today that sort of the state-of-the-art simulations and analytics are showing that this is a discontinuous transition. So if you're obviously at very low values of the coupling and even negative values of the coupling, which means anti-ferromagnetic interactions, you won't get any flocking. So if you measure the polar order parameter, which is this average particle direction, you will get 0. But as you come to reach a critical value of that coupling, if the coupling becomes stronger than the noise, so the misalignment that you get, you will start jumping to a finite value of that polar order parameter that then approaches 1 as K becomes larger and larger and larger, okay? So just note here, there's nothing particular with the fact that in the simulations I'm showing you, K is jumping right around 0. It's just because we placed ourselves in a very low noise limit. And so that critical value of K here is very close to 0. We don't need much strength to actually get a flocking state. But if we were at a larger value of that noise, you would get that transition to shift to the right. So you need stronger coupling to be able to overcome the noise and to be able to get the emergence of these flocking states. Okay? So that's all sort of 30 years ago physics. But since then, there's been a lot of work that's been done, and what's been discovered over the past 30 years is that in many ways flocking is both more robust and more fragile than anybody could have anticipated. More robust in what sense? Well, there was a good example from Rob this morning about the fact that flocking can emerge in systems where there's actually no alignment interaction. Okay, I could have picked the picture from your simulation, but basically this is an experimental realization from the group of Olivier Dochot and works with Hugues Chatet, where you do actually see collective motion. I don't quite know where the video stopped. But you do see these swirling patterns in quite a lot of collective motion, even though these are only purely repulsive particles. They are spherical, and so there shouldn't be any alignment interactions between them. And then there's been a lot of other works over the past 30 years that have been showing similar results. They're also more robust because the physics of flocking has been shown to be insensitive to the exact details of the alignment rules. So you can do that min sign, or you can do just pure sign interactions, you'll get flocking. But on top of that, it doesn't have to be metric interactions. So these interactions that stop at a given distance, you can do topological interactions, for example, and you'd still get flocking. So there's very nice work by David Martin recently that is actually sort of convincingly showing that metric or topological interactions lead asymptotically to exactly the same flocking physics, okay? And the flocking physics we're talking about is basically a separation in between, well, transition in that phase diagram here in between a disordered state, so a state that is not flocking, to an homogeneously ordered state that's separated by a band, a traveling band that is dense, surrounded by a disordered gas, because we're talking about the discontinuous transition here. But in many ways, flocking has also been shown to be a lot more fragile than we were expecting. There are very beautiful recent simulations, very large-scale simulations with millions and millions of particles from the group of Uxate, who've been showing that if you just take a system which here is all flocking in one direction, so the color you're seeing is the direction of the particles, and you add in that homogeneously flocking state a small physical obstacle, that's enough to destroy flocking. So let me just play the video for you. You see that all the particles at first were moving to the left, and at some point that obstacle is enough to actually nucleate a reversal wave that completely breaks apart the homogeneous, this homogeneous ordered liquid. In a sort of similar way, it's been shown that spatial anisotropy and dissenters, so particles that would be sort of antiferromagnetically interacting with the flock, are also enough to disturb flocking. And finally, in models of where you've got a discrete symmetry, so for example, think about the active Ising model that has been shown in part this morning, people have also showed that these discrete symmetry flocks display metastability, where even if you start from a system which here is moving, so dark colors is -1, so it's moving to the left, at some point there can be spontaneous nucleation of a small part of the flock reverting the direction, so moving towards, so it will become a red, moving to the right. And after the nucleation, you see the growth of this particular reversal wave that will eventually take over the system and make the system flock to the right for some time, and then another one will nucleate, making the system move to the left. So flocking is probably not as, a flocking phase is probably not as stable as we originally thought. Okay, so based on all these observations, we asked a relatively simple question, which we were surprised nobody had really looked into when we started, which is that most people have only studied one population model where everybody's interacting the same way with their neighbors, but that's probably the exception rather than the rule in nature. There's no reason why in a natural flock every bird aligns the same way with every single neighbor. You know, birds may have their preferred mates, who knows? And so they may be more likely to interact like these two strongly, these two not so strongly, and these guys here can't see each other, so they will try to anti-align as much as possible. Allowing this type of freedom means that we need to have a pairwise type coupling, which is not a constant anymore, but can vary. Inspired by, so that's the original active model that I put there again. We are going to be releasing the constraint that k is a constant, and inspired by spin glass physics, what we're going to say is that these couplings, these kij's here, they're going to be Gaussian distributed, normally distributed, with a mean k bar. So we'll have a mean coupling strength k bar, and a standard deviation for that distribution sigma k. Okay, so from basically a delta Dirac at k, we will go to something which is spread in that k space. That can be centered on 0 if k bar is equal to 0, but doesn't have to be. Okay, so we could look at distributions like the green one that you see here, where you've got a k bar that's positive with a non-zero sigma k, but we can also look at distributions where k bar is negative. And so the majority of the interactions are actually antiferromagnetic in the system. So we've got a model, let's just put it on the computer, let's see what we get. So what I'm going to be showing you in a second is basically that exact same plot that we had before, the polar order parameter as a function of that mean coupling strength for a variety of values of sigma k. Okay? Okay, polar order parameter is on the y-axis. You've got here the mean coupling strength k bar. And I'd like to draw your attention to the fact that you go from the light blue where you got sigma k is equal to 0. This is the original V-check model. And as you go to darker and darker colors, you're basically spreading and spreading and spreading your distribution. And what we got really surprised about is the fact that as we allow the distribution to spread, we are driving our transition to lower and lower values of k-bar. That could have been expected because we're allowing this distribution to be wide enough that some of the interaction strength will be very large, okay? But the surprising fact to us was the fact that you may get flocking in some cases, even when k-bar is negative. Meaning that most of the interactions in the system are antiferromagnetic, yet the system finds a way to still flock at a macroscopic level. So this is obviously run at a fixed value of the density, a fixed interaction radius, and fixed noise strength. Let me just show you a figure to actually show you that here, if we place ourselves at k-bar is equal to 0, so as many antiferromagnetic as ferromagnetic interactions, there shouldn't be any decision about whether I flock or not in a system where sigma k is equal to 0. Yet when I place myself at sigma k is equal to 8, you can see from this video there is clear flocking emerging, where here if you've got a polar histogram of the directions of the particle, it's quite clear that they quickly decided to go towards that 130 degrees, 135 degrees direction and stayed there the whole time of the simulation. So let's vary a little bit the parameters. We had not actually seen sort of a complete phase diagram from even the original VCheck or flying XY model. So we redid it with sigma k is equal to 0. You've got here k-bar varying, and here the density in the system. So as you go to very, very small density, birds can't find each other because here we're working at fixed value for the interaction radius. They can't find each other, so you're not expecting any flocking to be happening, okay? Flocking is yellow here, that's a high value of the polar order parameter. And as you go up in density, well, you go to something that's basically becomes independent of density. You've got one value of the critical strength, the critical interaction strength, k-bar, okay? And in the case where you've got some noise in the system, well, if I draw a line here at k-bar is equal to 0, you will see that it's happening at some positive value of k-bar, or I say k-bar, but here would be k because it's a delta function. Now, if I go to I switch that coupling disorder, that quenched coupling disorder, and I actually look at a case where sigma k is equal to 8. What I see now is that I've got an excursion and a reentrant behavior. As I'm at low density, the same sort of story prevails. You cannot find your neighbors. If you can't find your neighbors, then there's no emergent behavior. But at high density, really high density, you get to the limit of a min-filled glass, and the limit of a min-filled glass in this particular model tells you that there is no non-zero magnetization, so we're expecting that this would actually keep on going down as you keep on going and going and going to high density. So that's we think the sort of physical reason why there is reentrant behavior in terms of density here. And if I do the same game and I draw my k bar is equal to 0 line, we see that there is quite a large swath of the parameter space which has non-zero flocking, so non-zero polar order parameter, non-trivial flocking here, but is at k-bar negative. Okay? So I can do that game as well by varying continuously sigma k, and we get this sort of surface where inside here we find a polar ordered state, and outside of the surface we find a disordered state, and the size of the region which is at k-bar negative, but we still get flocking, is actually getting larger and larger as sigma k is increased. Okay? So the question is, what sort of physical mechanism may be behind this? Just as a quick note on in passing, we've actually gotten so sort of surprised about that counterintuitive result that we decided to test it for topological interactions, and the same picture stands. And we've tested it as well for a sort of weighted bimodal distribution. So here we just have two delta peaks at a negative value and a positive value, and the relative weights tell you how many particles are, how many interactions are ferromagnetic or antiferromagnetic, and we get the same picture as well. Okay, so it has nothing to do with the fact that it's Gaussian distributed. What I would like you to take home with you is the fact that the way we're understanding this problem at the moment is that self-organization and local clustering in your system are key to your system self-organizing into pockets or clusters of particles that really interact well with each other. And so while in a spin glass you're fixed on a lattice and you will get frustration no matter what you do, here the system finds a way to kill off that frustration to be able to have non-zero magnetization arising. So let's try to see how we can see that from the data. So what we've done is simulations here at a low value of sigma k. You see that the system is quite homogeneous in density at larger values of sigma k at the same value of k bar. So here is k bar is equal to 0, just as an example. You see that you got a lot more clustering, even visually in the system. We can quantify this by looking at the distribution of the number of neighbors. And you see it evolving here from the Vicek case, which is in green, to a slightly heavier tail here for the case where you've got sigma k is equal to 1, and this spreading even further, so you've got larger clusters being formed for sigma k is equal to 8. Okay? Another way to visualize it is to look at a 2D histogram, where what you do is you're plotting here the weight of finding a particle at a particular distance rij with a particular coupling strength Kij. And we've just normalized it by sigma k, so we are able to compare the case sigma k is equal to 1 and sigma k is equal to 8. And what's quite clear from these two pictures, maybe not so much on the left, although you can start seeing it, but really is clear from the picture on the right, is that within the interaction radius, which we've set in the simulations to 1, the system is self-organized in such a way that you've got mostly people that you're ferromagnetically interacting with next to you. Okay? Okay, so just to classify a little further the state of the systems we've been looking at, we've thought about looking at what we call a demixing order parameter. So this order parameter here is basically the ratio, the average ratio of number of neighbors that are ferromagnetically interacting with you, because Ni is the total number of neighbors, and so 0 will tell you that you've got about as many ferromagnetic and antiferromagnetic particles around you. Anything positive, more ferromagnetic particles. Anything negative is less ferromagnetic neighbors. And so we can draw these sort of diagrams for the same state space, rho versus k bar. And you can also look at the density correlations to be able to quantify clustering. So you basically do this connected density correlation. We can draw a threshold and actually ask what is the value RC here at which it falls below some very small value, and we can do that to extract a typical cluster size. I'm going to pass quickly on that, but just to say that we put all of these together on the same phase diagram. Here you've got in green the line that is telling you that you've got a transition from disordered state to an ordered state. The red line tells you that this is concomitant with a demixing, where your neighbors now become more likely to be ferromagnetically interacting with you than antiferromagnetically interacting. But what is surprising to us is that much earlier in terms of k-bar in the system, although you're completely disordered, you've got non-trivial clustering. So you've got small clusters that are actually forming, so you've got structuration in the gas, and yet not yet any demixing. The transition to flocking is a combination of both that clustering, that will eventually become bends and then an homogeneous liquid, but also of that demixing, of that self-organization in terms of interaction strength. So just to finish, that's the sort of phase diagram that we sort of propose here, where you've got in dashed line the original Vicek picture. As you turn on sigma k, you get that reentrant behavior. All the green phase here is non-trivial polar order. Outside, you've got a disordered state, but as you're approaching that transition, you get more and more spatial clustering in it. And just so that we confirm that we get the same sort of physics, what you see inside this region is really something where you've got no polar order. Here either, yet you get a little bit more clustering. You see even visually that there's more clustering. Deep in this phase, you'll see your homogeneous liquid. You see that all these little arrows are pointing in the same direction. It's an ordered state. And somewhere in the middle, we've confirmed they're hard to see and harder to get than in the original Wittek model. But we've confirmed with these chromographs that we also see that bended phase. We also see the bends happening. So we believe that the nature of the transition hasn't been changed by that quench disorder. So I'll just leave the summary right here with basically the main message from today is the fact that, strikingly, it seems like quench disorder at the level of the interaction, the coupling strength, does not seem to be destroying flocking, but rather seems to be promoting it, which is something that we found quite counterintuitive in the first place. And the two key ingredients are this self-organization and that spatial clustering that seems to be happening ahead of that flocking transition. If you're interested in it, you've got here the link to our archive submission. As I said, it's been up there for only a couple of weeks. Please, we welcome any feedback or comments. And with that, I'll just thank again my collaborators. So Eloise is right here, Raphael and Sylvia, and thank you for your attention.
The talk. We welcome any questions while we get ready for Venkata. The first lightning talk sets up. Any questions in the room?
Very nice talk.
Thanks.
And if you can come back to the video, to the movie of the blocks.
Yep.
I had a feeling that the system stands for organized in few independent blocks, which could be a way to.
It's. I think it's the. I see where you're coming from. We've gotten really confused about that as well. So you're talking about this video, right? So
Yes.
So if I play this video, you're telling me that it seems like you've got a secondary flock that's basically crossing. Sorry. Look at the polar histogram. There's nothing like that, right? So I think it's just a visual sort of artifact. You're being sort of biased or being trapped by the video because the polar histogram, and that's the reason why we're putting it here, is not showing any bimodality. So you would see two lobes if we really had two flocks crossing each other.
Maybe a quick other question.
I wonder if like a really interesting parameter to look at would be the average time it takes to find your like best friend, which would be the person with exactly the same polarization as you, but can not polarization, but coupling as you, but contains you.
That you
right?
couple with.
Like that time to find them.
So we haven't looked at that. I think
Yeah.
that's a good question. What we've looked at is typical contact times for any pairs of particles. And there's something that's a little bit mind-boggling there to us, is that although we get clustering before we get flocking, there doesn't seem to be any signature in the distribution of contact times before you get emergence of flocking. So you get clustering, but these clusters are very dynamical. They're basically just crossing, and we assume there are events that are coming from the fact that because you've got a distribution of couplings, you've got really, really, really high values of couplings when you get large sigma k. There may be these events that are spuriously just aligning you, keeping you together for a split of a second, couple of images on your simulation, and then make you leave. But these don't have enough weight to actually be showed in these distribution of contact times. We've done Kullback-Leibler divergence to check the differences in the distributions, and we basically get zero until we get flocking.
I wonder if that's finding people who are similar to you but not exactly the same, and then you find your best friend and then you stick with them.
Could be that. Yeah, I don't know.
If you have any other questions, I've also got a poster later, so see me or
Nice
later.
plug.
But yeah, let's thank Thibault and